Hold on one. All right, go ahead whenever you're ready.
My first question is on page 173, 6.5.
Okay.
And similar questions for when. Okay, maybe this one isn't this. Nope, I'm sorry, 6.7.
Okay. All right, so state the number of protons and electrons of each of the following. All right.
Yeah.
So keep in mind that for ions, the number of protons stays the same,
Okay.
as with the atom itself, as compared to the atom itself. But the number of electrons will change. Okay, so that's the part that's going to change, because essentially the identity of the element is going to stay the same. So the number of protons is going to have to stay the same, but the number of electrons will change. Now, if electrons are gained, that will give us a negative ion. So in other words, it'll give us an ion with a negative charge, which we commonly call an anion. Because if you're gaining electrons, the idea is that now you're going to have more electrons than protons, so the overall charge adds up to be a negative number.
So those would be in group 5A, 6A, and 7A.
Correct. So
Okay.
if you think about in the periodic table, the A group elements essentially only form one particular ion. And the goal in terms of chemical bonding in general is to satisfy the octet rule, which for most elements is to get to 8 valence electrons. So the idea for the most part is that for nonmetals, the easiest way to satisfy the octet rule is to gain electrons. So that's why you see for the nonmetals, they tend to form ions with a negative charge. Now, for the nonmetals in group 5A or 15, the ion that you're going to have is one that has a -3 charge. Because the general idea is that they have 5 valence electrons. And remember, valence electrons are the electrons in the outermost energy level. Those are the ones that are involved in chemical bonding. Basically, they have 5. The goal is to get to 8. I usually tell students, just based on common sense, what's the easiest way to get to 8 valence electrons? Is it to lose 5 or is it to gain 3? The easiest way to lose valence, to get to 8 valence electrons is to gain 3. So if you're going to gain 3 valence electrons or 3 electrons total, hi Geraldine, you're going to have a -3 charge associated with you. So those are for the nonmetals in group 5A. For the nonmetals in group 6A or 16, the type of ion you tend to form is one that has a -2 charge. Because if you have 6 valence electrons and the goal is to get to 8, what's the easier thing to do? The easier thing to do is to gain 2 instead of losing 6. So they tend to form -2 ions. And then for the halogens in group 7A or 17, the type of ion they tend to form is one that has a -1 charge. Because they have 7, if the goal is to get to 8, do is to add 1. So the general thing about nonmetals is that nonmetals will gain valence electrons in order to satisfy the octet rule. And that's why they form those negative ions. Now, on the other hand, if electrons are lost, now you're going to have a positively charged ion, which is what is known as a cation.
Okay.
And what we find is that metals tend to lose valence electrons to become positive ions in order to satisfy the octet rule. So for the metals in group 1A, or 1, and this would include hydrogen as well. So including hydrogen, which of course is a nonmetal, but it's in group 1A. they tend to form a +1 ion. Because for most of them, if the goal is to get to 8, there's essentially, in theory, 2 possibilities: gain 7 or lose 1 and go back to the next lowest energy level, which has 8, which is sort of the easier pathway. The easier pathway is to lose 1 and then go back to that lower energy level that already has 8, so that the octet rule would be satisfied. Now, for the metals in group 2A or 2, they tend to form a +2 ion. And then basically for aluminum in group 3A or 13, which is the only essential metal in that area, aluminum forms a +3 ion. So we can use the periodic table for most of the elements for the A group elements, for a lot of them, to predict the type of ion they're going to form. But the general idea with ions is that the number of proton, when you go from atom to ion, the number of protons stays the same, but the number of electrons will change.
Okay.
So you want.
So my questions are the ones that have the transitional metals.
Okay. So
like A.
Yeah. So, but for this question here, 6.7, it really doesn't matter if it's an A group or a B group.
Okay.
Basically, we're just going to look at the periodic table, and we're going to use the charge that they're giving us for the element in this case, and they're telling us that copper is, in this case, the copper 2+ ion. So
Plus,
copper
okay.
has an atomic number of 29. So that tells us that we have 29 protons. But now, what about the number of electrons? If the charge is +2, that means that that ion should have 2 less electrons.
Because it'd be easier to lose 2.
So that's a great point. The Bs are a little bit different because for a lot,
Okay.
we're talking about orbitals that are like d orbitals and such like that, and it's a little bit trickier because
Okay.
for them it's not as simple as like going up to 8 or back to 8. It's a little bit more detailed than that.
Okay.
So the simplest thing just to say here is with the transition ones,
Okay.
a lot of them form multiple ions for reasons that the book, and we probably won't even touch upon too much. The nice part about that is you saw in the naming, you're actually given what the charge is because they can form multiple ions. But here, it doesn't make a difference if it's A or B.
Okay.
The fact that we're dealing with the copper 2+ ion tells us that this ion should have 2 less electrons. So in this case, the number of electrons is going to be 27. And if you think about it, if you have 29 positives and 27 negatives, that essentially adds up to +2.
Okay.
So how about B? So B would be selenium -2. So again, want to use the periodic table, and we find that selenium has an atomic number of 34. So that tells us that the ion has to have 34 protons. Now, what about the number of electrons? Since this is a negative ion, it should have 2 additional electrons. So
Okay.
in this case, instead of subtracting 2, we're actually going to add 2. So the number of electrons here would actually be 36.
Okay.
Okay. Okay. Okay with that question? Do you want to do more of that?
Nope, that one's good. Yep.
Okay.
My next one, and I kind of posted this on the discussions and I didn't really see if anyone answered it. I said first halogen gases, but I really meant noble gases. So this is 6.15 on page 176. we're saying whether it's an ionic compound. It's D, sodium and neon,
So,
which sodium is a metal.
okay, correct. So here's the thing. So the noble gases, okay, basically for them, the octet rule is already satisfied when they are atoms. Because for helium,
Oh.
helium
That's
has,
why they're in group 8.
well, one of the reasons, yep.
Okay.
So helium has 2 valence electrons. But remember, for helium, the highest energy level that it has is the first. So basically, its highest energy level is filled with those 2 electrons. Now, for the rest of the noble gases, they already have 8 valence electrons. So here's the thing. They don't want to gain, and they don't want to lose electrons.
Okay.
Because if you think about it, why would they? You know, if the goal of chemical bonding is for elements to satisfy the octet rule, well, if I already have the octet rule satisfied, basically leave me alone. You know, I don't want to gain, I don't want to lose. Now, noble gases on occasion will share, because one of the things with covalent bonds is that when you share electrons, they count for both atoms that are sharing them. So they're okay with sharing, but they definitely don't want to gain and they don't want to lose. And essentially, the noble gases don't form ions. So in terms of 6.15D, where you have sodium and neon, my answer there would be no. You know, that combination, even though it's a metal and a non-metal, which is sort of the trigger for an ionic compound, because neon is not going to want to give up any of its valence electrons, you're not going to get an ionic compound of sodium and neon. I'm sure somewhere out there there's probably an exception, but I'm not aware of it. You should not get an ionic compound at all with any noble gas,
Okay.
with any of the noble gases, because their octet rules, their octets, in a sense, are essentially already satisfied.
Gotcha. Okay, that makes more sense. My next question is on page 180.
Sure.
Geraldine, did you have a question before that?
No, actually, that was one of the questions that I have for this chapter.
Okay.
Because I was
Mine
really
is-
confused when I was doing the homework. I couldn't figure it out.
Yeah, I keep going really far, and then there's a point where I can't do it. And it's 6.27. And it's D.
Okay. Okay, ALP.
Yeah.
So, pretty
We're trying to find the,
you want the charge of the cation. So they want to know what the charge
Yeah.
of the positive ion is. So basically, aluminum is in group 13. Or
oh, okay.
it's okay. Because I know why. And we'll talk about it. The chemical formula there is strange in a sense, because
Okay.
you know, could you really have a chemical formula of ALP? And the answer is actually yes, and I'll show you why in a minute. But yeah, because aluminum is in group 13 or 3A, it's got a +3 charge. Now, the way that this works out is that if you have aluminum with a +3 charge, phosphorus always has a -3 charge. So the way I say it is, okay, how many of each
Oh,
you need to get the overall charge to add to 0? And the answer is you just need one of each. Because if you have one of these, of each of these types of ions, then the overall charge adds to 0. And that leads to the chemical formula of ALP.
all right. So let's back up and do like A.
Okay,
'cause-
so AU, because now you're dealing with a transition element. AuCl3. Okay. So here's how we want to handle it. I look at the chemical formula, and the chemical formula tells me I have one gold ion. But because gold is a transition element, I can't just use the periodic table to predict its charge. The chemical formula tells us that we have 3 chloride ions. Now, since chlorine is in group 17 or 7A, we absolutely know what the charge of each of these ions have to be. Each one of them has to be a -1 charge. Chlorine only forms one type of ion. It only forms an ion with a -1 charge. Again, at the end of the day, the sum of the charges has to add up to 0. So if the sum of the charges are going to add up to 0, what does the charge of the gold have to be here? It has to be +3.
So I did that cross and drop.
So the
And
crisscross,
did I just get lucky?
no, the crisscross method works.
Okay.
There's no doubt about that, it works. My concern with it is, go back to the example of ALP for a second.
Exactly. That's why I'm like, I did the cross drop and I didn't get the answer.
So here's the thing. If you were to do the crisscross method, just using the numbers, not the signs of the charges, you would cross the 3's to give you, AL3, P3. But what you have to do with the crisscross method is that if you have to find the simplest whole number ratio in order to have the correct chemical formula. So if you have a ratio of 3 to 3, you can simplify that to 1 to 1.
Okay.
And therefore, that gives you the chemical formula of ALP. That to me is the main drawback of the crisscross method, is that if you don't have the simplest whole number ratio, you have to remember to simplify it to the simplest whole number ratio. That's why for me, I kind of like to do it this way.
Yeah.
Because then I just basically figure out, how many of each do I need to get the charge to add to 0, and then I just write the chemical formula.
Okay.
I want to look at B because I think B is a really good example also.
Yeah.
Right? So Fe2O3. The chemical formula tells us that we have 2 iron ions. I don't know what their charge is yet because it's a transition element. The chemical formula also tells us that we have 3 oxygen ions. Now, because oxygen is in an A group, it's in group 16 or 6A.
6. Okay.
You know what the charge of oxygen is going to be in the ion form. It's always going to be -2. So now the question is, what do the charge of each of the iron ions have to be in order for the charge to add to 0? And one thing to remember is that the charges for the 2 ions have to be the same. You can't have different ions in the same compound. So if this adds up to -6 in terms of charges, this has to add up to +6. So what do the charges on the 2 irons have to be? They both have to be +3.
Okay.
Because now the overall charge will add to 0.
Okay.
Can you repeat that again? I'm sorry.
It's okay. So at the end of the day, the sum of the charges has to add up to 0 for any compound, whether it's ionic or covalent. So we use the chemical formula to tell us that there are 2 iron ions and there are 3 oxygen ions. We don't know from the periodic table exactly what the charge of the iron is because it's a transition metal. And transition metals could have multiple, they form usually more than one type of ion. But for oxygen, we know what the charge of oxygen has to be. It has to be -2. So that means that the charge of the oxygens adds up to -6. And therefore the charge of the irons has to add up to +6. So in order for that to happen, and since I have 2 of them, the charge of each has to be +3. The key thing to remember is that the sum of the charges must add up to 0 for all compounds. Because at the end of the day, all compounds are neutral, whether they're ionic or covalent. All right. Where would you head?
Okay, I see.
Whenever you're ready.
All right, so I think that, so this is D, that 3:3 ratio to the 1:1 ratio happens again on 6.29E.
Yes, it does.
Okay,
You have here gold, 3 nitride. So gold, chemical symbol of Au, because it's a transition element in the name, there should be a Roman numeral indicating the charge, and there is. The charge is 3.
3.
And I know it's positive because metals have to have a positive charge. So even though there's no sign there, I know the charge has to be +3. Nitride, nitrogen. Well, nitrogen is in group 15 or 5A. So nitrogen has a -3 charge. Now you're 100% correct. If you do the crisscross here, you're going to end up with Au3N3, but that is not the correct chemical formula because the 3:3 ratio can be reduced to 1:1.
Okay.
Therefore, the correct formula would be AUN.
So the question before was trying to have me find Au +3, that D.
Question before. 6.28?
27.
7.
Sorry, I'm just saying the question before that we just worked on D.
Yeah, so in that one,
Okay,
find, because in that case, we were going from chemical formula to name.
okay,
Therefore, we had to indicate the charge as part of the name. So we had to do some little bit of extra work there.
okay.
Here, we're going from name to chemical formula. So you actually luck out a little bit because the name has some extra information that
Right.
compounds don't have in their name.
Okay. This is a formula. And this is a find. So the one before we were finding the chemical, we were finding what?
For
The
6.27?
symbol?
For 6.27?
Yeah.
We were finding, I see what you're saying now. So, okay, my apologies. So if we were going to name this, let's do it that way. Because you're right, for
Okay.
6.27, we were just trying to figure out what the ion was. But now,
Correct. Just what the symbol ion was. Okay.
But now let's take it to the next step and name it. So we figured out that we would have 3 chloride ions and 1 gold ion, and that the charge of the gold had to be +3. So to write the name, we would have gold 3 chloride.
Okay.
Got to give the Roman numeral indicating the charge next to the name because it's a transition element. We did Fe2O3. Based on the work we did, that compound would be iron 3 oxide. Because again, iron is a transition element. We did the work to figure out what the charge of the iron ions were going to be. So we have to include that in the name. So that would be iron 3 oxide.
Okay, so let's do one more.
Of course.
It's 6.31 B to where it has a 4-to-2
Okay.
relationship. So then I don't know what to do there.
So, sorry, lead 4 oxide. All right.
And I believe I'm writing the formula.
You want to write the chemical formula. So
Okay.
chemical symbol of Pb, it's a transition element. They tell us in this case that it has a +4 charge. Oxygen, O. We know for oxygen, ion, always -2. Now you're right. If you do the crisscross,
From the group.
right, because it's in group 16 or 6A, so the charge is always -2. Now, if you do the crisscross, you'd end up with Pb2O4. But now my follow-up question would be, is that the simplest whole number ratio? If you have 2 to 4, can you reduce that into something simpler? And the answer is yes. 1 to 2. So in fact, the correct chemical formula would be PbO2. Now, just to show you the way that I would have figured that out would be, once I established my 2 ions, my follow-up question would be, how many of each do I need to get the overall charge to get to 0?
Right.
All I need is a second oxide ion. 1 lead, 2 oxygens, PbO2.
Okay.
That's sort of my tip in terms of how to, but again, if you're comfortable with the crisscross, it's great, it works. You just have to remember to simplify, if you have, any like 2 to 2, 3 to 3, 2 to 4. I don't know if you'd come anything outside of that. I think those are the 3 ratios that you'd have to remember and remember to simplify, so to speak.
Okay. Okay, let's do one where it has the chemical is a poly.
Polyatomic ion.
Yeah, so it's a 6.41. And the charge is in the parenthesis.
Okay. So which one do you want to do? A, B, C, D?
D.
Okay. Now, a couple things. So this is zinc phosphate. All right. One of the things with the polyatomic ions, there's a lot of them. I wouldn't memorize all of them. I think that's just taking up time that you could really save. If you look at the table 6.8, there are certain ones that are in bold. Those are the ones you need to know. And honestly, those are the ones that you come across the most often.
Yeah.
I mean, nitrate, chlorate, carbonate, sulfate, phosphate. I think to memorize all, what is it, like 20 of them on there? I think it's a little bit much. So I would say, look, if you know those in the bold, you're going to be perfectly fine with the polyatomic ions. Now, the other thing is there are certain transition metals that only form one type of ion. And because of that, there's no Roman numeral indicating the charge in the name. So I'm going to give you these three. There's only three of them, but you sort of have to remember these three. One of them is zinc. The only ion zinc forms is an ion with a +2 charge. The second one is cadmium. The only ion cadmium forms is one that has a +2 charge. And the third one is silver. The only ion silver forms is one that has a positive charge. And again, the reason why you basically have to know those is because there's no Roman numeral given in the name. So if you don't know what their charges are, you can't answer the question.
Okay.
Right.
I thought in the book it said that silver had a +3 charge.
I'm going to
Did I
double
write that wrong? Is that gold?
gold. Yeah, you're looking at gold.
All right, I got those two mixed up.
Okay. Yeah. I only really remember, I mean, off the top of my head, because I just had this discussion with a couple people the last couple of days. So it's sort of less in the mind. But yeah, gold could form +1 or gold could form +3.
Yeah, because I watched it on the video, the modular, and I'm like, what? I thought the book said that I had 2 of those. So, okay.
So yeah, silver only +1. So for zinc phosphate, couple ways to solve it. Zinc would be +2. Now, if we look up phosphate before we have it memorized, phosphate has the chemical formula of -3. So if we wanted to do the crisscross, which we can, we would have 3 zincs. Now, when you have more than one of a polyatomic ion, you have to put the polyatomic ion in parentheses with the number of it that you have as a subscript on the outside. So in this case, you'd have to put a 2 on the outside.
So then here you don't try to simplify trying to get the whole, I wrote it down.
Right, because in fact, 3 to 2 or 2 to 3, however you want to look at it, is the simplest whole number ratio. Because the only thing you can get smaller than that is 1 to 1.5. And that's not a whole number ratio because you don't have decimals in chemical formula.
Right. So what's confusing me is that 4 and the 2.
So think about it this way. One of the ways to look at the polyatomic ion is as a single unit.
Okay. So you can't separate them.
Can't separate it. So PO4 stays together. So essentially, if we were to sort of, look at this a little bit deeper, you would have 3 zinc ions and you would have 2 phosphate ions. But every time you have phosphate, it's
6.
PO4.
Oh.
It never changes. So, you could change the number of them that you have, but the polyatomic ion itself never changes. That's why some people say, treat the polyatomic ion as a single unit.
Yeah.
And in this case, you'd have 2 phosphates, and that's why you have the 2 on the outside. But when you have more than one of a polyatomic ion, it's got to be in parentheses with the subscript on the outside to indicate how many of those ions that you have.
Okay. All right, so we're on that chart.
Okay.
It's page 185,
Okay.
6.43.
Which letter do you want to do?
I got C. It's the only one I got done.
Okay. All right. So let's look at the rest. Not a problem.
Okay.
So 43A. They want the formula for the polyatomic ion and the name of each of the compounds. Okay. Na2CO3. Name is actually probably the simpler part. Na is the chemical symbol for sodium. CO3 is the chemical formula for carbonate.
Carbonate, okay.
Therefore, this compound would be known as sodium carbonate.
Okay.
Now, a couple things. You can memorize carbonate and know its charge, but let's say you didn't. Based on the chemical formula, we have 2 sodium ions. From the periodic table, we know that sodium has to have a +1 charge. From the chemical formula, we know that there's 1 carbonate ion. In order for the overall charge to add to 0, what does the charge of the carbonate have to be?
A -2?
There you go. And that's actually the
Okay.
exact formula for the carbonate ion.
Okay, yeah, that's what I'm missing. I was trying to do the crisscross,
It's
but how would I know that it was going to be a negative? Do you see what I'm saying?
So here's the thing. In this case, you sort of would have to do a reverse crisscross.
Mm-hmm.
Here's how you would know. The metal always has to be positive.
Oh,
Most of the time, like 95% of the time, the
okay.
atomic ion is going to be negative. Or the other way
Okay.
to say it is, and maybe this is probably even the better way, whatever comes first in the formula has to be positive. Whatever comes second in the formula has to be negative.
Negative. Okay.
That's probably even more accurate.
But if I would do that one process, rewrite it out and try to make it equal to 0.
I just think it's, as I said, students have been very comfortable with the crisscross.
Right.
It works. That was the way I was taught it way back when. But I've just found over the years that it's just sort of a clearer explanation to write it out and to see that how many do you need to get the overall charge to add to 0.
Yeah. I mean, I could definitely see it was -2 because I have a +2. So the opposite is -2. And here I'm still wondering, where did they get that 2? Well, okay, I know where they got the 2. I just don't know where they got the negative.
And that's
So,
and this is it. You as you said, you need 2 sodiums, Na2, and you need 1 carbonate, CO3.
Yeah.
There's your chemical formula.
okay.
All right.
Can we
B.
do B?
Which one?
B?
B, yes. So NH4, 2. F.
2.
All right, so this is like the one polyatomic ion that's actually positive. This one is ammonium, and then S would give us sulfide. So the name of this compound is going to be ammonium sulfide. Do you have to memorize ammonium? I would say no. But NH4 as a polyatomic ion is what is known as ammonium. Now, let's figure out the charge of ammonium. So based on the chemical formula, we have 2 ammonium ions. We don't know what its charge is. Based on the chemical formula, we have 1 sulfur ion. Because sulfur is in group 16 or 6A, sulfur has to have a -2 charge. Therefore, in order for some of the charges to add to 0, what charge does each of the ammonium ions have to have?
A +1?
+1, that's right. Because +1 gives you +2, +2 and -2 gives you 0. So as it turns out to be, if you were to look up the ammonium ion, you would see NH4 plus. That's the formula for the ammonium ion.
B. Okay.
Let's look at D. So SN, NO2, 2. So, couple things. SN, chemical symbol for tin. Now, Because tin is in the B groups, we're going to have to give a Roman numeral giving the charge. NO2, if you look at the list of polyatomic ions, NO2 is nitrite. Now, in this case, in order to figure out the charge of the tin, we have to know what the nitrite ion is. We can't figure out the charges for both. By definition, nitrite, its chemical formula is NO2 minus 1. Just like for ammonium, by definition, it's NH4 plus 1. Just like for carbonate, by definition, it's CO3 minus 2. Therefore, since we only have one tin ion here, what does the charge of the tin have to be? Plus 2. Because if it's plus 2, and this adds up to minus 2, now the overall charge adds to 0.
Oh my gosh.
What do you have here? You have tin 2 nitrite.
Negative. Okay. Plus 2. Okay. All righty. I think the next question is on page 199. 6.77.
Use Vesper theory to predict the shape of each of the following. All right, sounds good. I wanted to talk about this a little bit anyway. All right, so 6.77. All right, so let's talk a little bit about Lewis dot or electron dot structures and Vesper theory. All right. So first off, with covalent compounds, we often draw what are known as Lewis dot structures, which show bonds, covalent bonds, and what are known as lone pairs of electrons. In terms of covalent bonds, you have single, double, and triple bonds. And the difference between them is the number of electrons that are being shared between the two atoms. In a single bond, 2 electrons are being shared. In a double bond, 4 electrons are being shared. And in a triple bond, 6 electrons are being shared. And it turns out that carbon atoms, and you're going to see this in a few weeks, can actually form single, double, and triple bonds between them. And covalent bonds are usually indicated by lines. 1 line, single bond, 2 lines, double bond, 3 lines, triple bond, where each line represents the sharing of 2 electrons. As I mentioned a little bit before, which is really important, shared electrons count for both atoms that are sharing them. So in other words, these 2 electrons would count towards the valence electrons of both carbons. These 4 electrons would count towards the number of valence electrons for both carbons. These 6 electrons would count towards the number of valence electrons for both of the carbons. shared electrons count for both atoms that are sharing them. Okay. So in 77A, we have what is known as GAH3. So how would we come up with the Lewis dot or the electron dot structure for that compound? All right, so here's how we do it. GA is in group 3A. So that tells us that it has 3 valence electrons. Hydrogen is in group 1A, and therefore it has 1 valence electron. Okay, so you have each of the hydrogens with their 1 electron, and then you have the gallium with its 3 valence electrons. Now, for hydrogen, the goal is to get to 2. And in this example, that goal can be met. Now, for gallium, for most of the elements in the periodic table in period 2 and beyond, the goal is to get to 8. However, there are some elements that are okay with having less than 8. And it turns out that gallium is one of them. And in this case, the gallium can't have any more than 6 based on the number of electrons that there are total. So how would each hydrogen get to 2? Each hydrogen would share its 1 valence electron with one of the valence electrons, or it would share its 1 valence electron with gallium, and gallium would respond with one of its valence electrons. And they're going to share 2 electrons between them, giving what type of bond? A single bond. So you end up with a single bond here, a single bond here, and a single bond there. And therefore, that is, in this case, the Lewis dot or the electron dot structure for GAH3. Now, from my perspective, to figure out the shape, we have to have this information. We have to see this structure. All right, now, essentially, Vesper theory.
So just real quick, that you said that GA is happy with just 3 or 6?
6 electrons, because if
6.
you were to count up how many valence electrons the gallium now has, and remember, shared electrons count for both atoms that are sharing them. This gallium now has 2, 4, 6.
6.
And for reasons that the book doesn't go into, gallium is okay with that.
Okay.
And the other part of it is that there's no more electrons that are present. So in this example, even if it wants to get to 8, which in theory it should, but it doesn't, it can't.
Okay.
It just can't, because there's no more electrons that are left. And remember,
Right.
you never have more than 2. So that's important as well.
Right.
Okay?
Yeah, I got that one, and I didn't even look at it, that it didn't even go up to the 8. So.
All right. So Vesper theory predicts shape around an atom, usually a central atom,
Yes.
based on the number of bonds and lone pairs.
Okay.
Now, the trick with Vesper theory is that it considers single, double, and triple bonds to be counted just as 1, so to speak. I don't know if you'll come across that too much, but it sort of considers single, double, and triples just to sort of count as 1.
Yeah, I think that's in B, the next one.
So we'll get to that.
Okay.
So if you look at gallium, gallium has 3 bonds and no lone pairs. After this, it's just basically once you determine that, now it's a memorization piece. Because what you have to do is you have to remember, what does Vesper theory say in terms of shape when you have an atom that has 3 bonds and no lone pairs? It says that the shape around that atom is trigonal planar. And honestly, that's just something you have to know from memory.
Okay.
Yeah. There's no other way I can sort of simplify it. You see the electron dot structure, and you see 3 bonds and no lone pairs, trigonal planar.
That's what it is.
Okay.
Okay.
B, OF2. All right. So oxygen has 6. Each fluorine has 7 valence electrons. All right, so let's talk a little bit about how this would first play out. All right, so 7 plus 7 is 14. So 6 plus 7, 14. It looks like we have 20 valence electrons total. Because we got 1 oxygen and 2 fluorines. So the oxygen's got to go in the middle. Put some dots around it. The fluorine's got to go on the outside. And those dots represent valence electrons. Now the goal for each of these elements should be to get to 8. And in fact, in this case, they can all get to 8. How would the fluorines, let's start with the sort of outer atoms first. How would the fluorines get to 8? Well, what they would do is that they would share one of its valence electrons with oxygen, and the oxygen would respond in kind. And if they're going to share 2 electrons between them, what type of bond are you going to get? You're going to get a single bond. The fluorine's now happy because the fluorine now has 2, 4, 6, 8 valence electrons. And remember, lone pairs, whereas shared electrons count for both atoms that are sharing them, lone pairs only count for the atoms that they're on.
So is that 3? Is that 3 lone pairs?
Yes, yes.
Okay.
So 2, 4, 6, 8, 3 lone pairs. Yes. So the fluorine on the right says, okay, I'll do the same thing. I'll take one of my valence electrons and share it with the oxygen to form a single bond between the oxygen and myself. And the fluorine is happy because the fluorine now has 2, 4, 6, 8 valence electrons. Now the oxygen has 4 more electrons that come along with it that are not used in bonding. So it has 2 lone pairs. And now the oxygen has 2, 4, 6, 8 valence electrons. So everybody's happy. But now what about shape? So what do we have going around on the oxygen? We've got 2 bonds. And we've got 2 lone pairs. So again, now comes a memorization piece. What does Vesper theory say for shape around an atom where you have 2 bonds and 2 lone pairs? The shape around that atom would be bent. The shape around that atom would be bent.
Okay. So it doesn't have a double bond then.
No.
Okay.
One of the things about halogens hate double and triple bonds.
Oh.
And in this case, you wouldn't need it because when the oxygen and the fluorines form their single bonds, they're all happy.
Okay.
Let's go on to C, because with C, we're not going to have all single bonds.
Yep.
HCN. Hydrogen has 1 valence electron. Carbon has 4. Nitrogen has 5. So We'll add that up just to count. And we've got 10 valence electrons total. So hydrogen, and actually let me draw it more on, let me give myself some more space. So we got hydrogen, carbon, and nitrogen. Okay. We know hydrogen wants to get to 2. So the simplest way for hydrogen to do that is to take its 1 valence electron and share it with the carbon to form what type of bond between them? To form a single bond. Now, what about the carbon and the nitrogen? They both want to get to 8. Can they get to 8? And the answer is actually yes. The way they can get to 8 is by sharing not 2 electrons between them, not 4 electrons between them, but actually 6 electrons between them. And when they share 6 electrons, what type of bond do you have? You have a triple bond. Now, what happens with the other 2 electrons on the nitrogen? They stay on the nitrogen. Now, is everybody happy? And the answer is yes, because the carbon now has 2, 4, 6, 8. The nitrogen now has 2, 4, 6, 8. Everybody's really happy. Now, what about shape? Well,
Oh, 1 lone pair.
the shape of this compound is going to be basically determined by the shape around the carbon. Now here you have a single bond and a triple bond.
Triple bond.
Here's where the idea of, in Vesper theory, single, double, and triple bonds are considered equivalent. Because what we would say is that here we have 2 bonds and no.
No lone pairs.
And when you have 2 bonds and no lone pairs, what is the shape around that atom? The shape around that atom is going to be
Linear.
linear. Correct.
Okay.
This sort of expresses, it's a good example to look at because it expresses the idea of how single, double, and triple bonds are considered equivalent to each other. Right? And then the last one, D, CCl4. So carbon has 4 valence electrons. Chlorine has 7 valence electrons.
10 by 4. 8.
Multiply that by 4 to give us 28. So we're going to have 32 valence electrons total. Always good just to keep a track of the total. The way it sets up, the carbon's in the middle. Each of the chlorines is surrounding it. So, can each of these atoms get to the magic number of 8? And the answer is absolutely yes. Based on what we've done so far, and you're looking at it, what do you think is going to happen in order for each of these atoms to get to the magic number of 8? Well, the carbon with each of the chlorines individually are going to share 2 electrons. Between the carbon and each of the chlorines, you're going to have single bonds. And that works out really well because now for each of the chlorines, if you were to count it up, each chlorine has 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Perfect. The carbon has 2, 4, 6, 8. Excellent. Now, what about shape? Well, in terms of shape, 4 bonds and no lone pairs. What does Vesper theory have to say? Well, it says the shape around that atom is tetrahedral. So really, it's about figuring out the Lewis dot structure and then using a memorization, a knowledge of Vesper theory around the central atom to predict the shape.
The central atom, that's the thing.
That's the key.
The one before, I thought there was 2 lone pairs, so
Yeah, but it really would shape
it's that central atom.
that central atom. Yeah. So it wouldn't be in the previous example, it's not about the hydrogen, it's not about the nitrogen, it's about the carbon, because the carbon's in the middle. And usually the examples that you have are more like CCl4 or OF2, where it's obvious, sort of what's in the middle. When we get to the second half, like organic part, you're going to see multiple carbons and essentially multiple central atoms. But I think at this point, the examples that I'm looking at here really have a single central atom, and that will determine the shape of the compound.
Okay. All right, my next question is 203. This has to do with the attractions.
Okay. So
6.81, identify whether it's a polar or non-polar.
all right, so let's start with that one. All right. So first off, your covalent bonds can be of 2 types based on the difference in electronegativity between the atoms. Remember, in terms of a definition, electronegativity is the ability of an atom to attract electrons towards itself. The reason why we have not only covalent and ionic bonds, but the reason why we have even different types of covalent bonds in terms of polar and nonpolar is based on differences in electronegativity. In your nonpolar covalent bonds, the electrons are shared equally, which means that the atoms really are neutral. You have this when the electronegativity difference between nonmetals is 0 to about 0.4. So if you have 2 nonmetals whose electronegativity difference is somewhere between 0 to 0.4, more likely than not, especially if it's 0, it's going to be a nonpolar covalent bond. So the electrons are going to be shared equally, the atoms are technically neutral. The other type of covalent bond is a polar covalent bond. Now here, the electrons are shared unequally. And the atoms are not technically neutral. Because, one of the ways to think about it is sort of like a tug of war. I like to think about a covalent bond as the 2 teams holding onto the rope and the flag indicating where the electron density is in that bond. In a nonpolar covalent bond, the two teams are pulling with equal strength. So the flag stays in the middle. But in a polar covalent bond, one team has a little bit more strength than the other, so that they're still both holding onto the rope, but the flag is no longer in the middle. The flag is closer to one team than the other. Now here, the electronegativity difference between the nonmetals is 0.5, I think, to about 1.7 in terms of an electronegativity difference. Okay. Now, in terms of compounds or molecules, compounds or molecules, and we're talking about covalent, can be polar or nonpolar. So bonds can be polar or nonpolar. Compounds, covalent compounds, can be polar or nonpolar. I think the easiest way to talk about it is the nonpolar scenario. Two things. First, the electronegativity difference between the atoms in all bonds is 0. So in other words, independent of the shape, if you have all the bonds in the compound that have an electronegativity difference of 0, the covalent compound is going to be nonpolar. That very rarely happens. The more often cause is shape. There are certain shapes where, and this is where sort of physics comes in, which is a little bit makes it difficult to sort of describe. But essentially, the polarity of the bond vectors cancel each other out so that the electron density is distributed symmetrically in the compound. The thing to remember is linear, trigonal planar, and tetrahedral. Those shapes, and the only caveat would be that all bonds to the central atom are the same. If you have these three shapes, the compound or the molecule is going to be nonpolar. But on the other hand, if it's bent or trigonal pyramidal, which I think are the other two shapes that are discussed, then the compound is going to be polar. So really, for the most part, it comes down to scenario 2. It comes down to shape. So if you look at A, CS2, here's the carbon, or here's the sulfur, 6 valence electrons. Here's the carbon. Here's the other sulfur. Again, so now it's like electron dot, Vesper, and then polarity. So this is like the next stage in the process. What would happen is each of the sulfurs would form double bonds with the carbon. And that ends up working out really well. Because that gives each element 8 valence electrons. Each sulfur has 2, 4, 6, 8, 2, 4, 6, 8. The carbon has, and I probably should have, let me just move these dots back to here to try to make it a little less confusing. So 2, 4, 6, 8, 2, 4, 6, 8, and the carbon has 2, 4, 6, 8. So now we go to Vesper. 2 bonds and no lone pairs. What shape would we have? Because again, we're looking at the carbon, the central atom. Linear. Now, what does that tell us about the polarity of this compound or molecule? It tells us that we're dealing with a nonpolar molecule. Even though these bonds are polar covalent, because of the linear shape, the compound is nonpolar. Any questions about that? Let's look at letter B. NF3.
So the step is to make it a Lewis structure,
Yep,
then that Vesper
yep. Then Vesper for shape.
for the shape.
And then remembering, again, some memorization, which shapes lead to nonpolar molecules versus which shapes lead to polar molecules. Okay. So here's NF3. The fluorine, each fluorine with the nitrogen are going to form single bonds. Each of the atoms can get to 8 valence electrons. The nitrogen is going to keep a lone pair. It's going to have a lone pair on. This pair of electrons right here, the nitrogen doesn't use to form bonds in this compound with. Okay. Now, what does Vesper theory tell us? 3 bonds and 1 lone pair. That shape is trigonal pyramidal. And because the shape is trigonal pyramidal, that leads us to that this is a polar molecule. The electronegativity difference between each of these is not 0. So because of the shape, we have a polar molecule. Okay. C, I wouldn't even worry about because that's getting a little tricky. Kind of unfair to throw C in there with the rest. Do you want me to do D?
Yeah.
So let's do D. All right. SO3. So oxygen, 6.
2 bonds.
Sulfur, 6. Okay. Let me just change this up a little bit. Okay. So, how is each of them going to get to the magic number of 8 electrons? This one, trying to think of the easiest way to explain this one. SO3. Each oxygen has 6. Sulfur has 6. So if we form okay. So the sulfur here is actually going to violate the octet rule. The reason why is because period 3 elements and above can actually do so, because they actually have d orbitals that are empty, that leads them to have space for more than 8 valence electrons. Period 2 elements can never have more than 8 valence electrons. Period 3 elements usually want 8, but they can actually go above and beyond.
Wow.
The reason why I have to mention that here is because in order for each oxygen to get to 8, which it can do, you actually have to have double bonds between the sulfur and each of the oxygens. And that actually gives the sulfur 12 valence electrons, which sulfur is actually okay with, interestingly enough. So I guess you'd have sharing that way, sharing this way, and then sharing this way. Because in order for the oxygen to get to 8, it's got to have double bonds. And the sulfur can actually be okay with having all double bonds with the oxygens. So that would be a little bit of a tougher one to figure out. Fair enough. But if you're able to get to that, now we get to, for the sulfur, 3 bonds and no lone pairs. So what shape would you have around the sulfur atom? You would
Trigonal planar.
planar, which
Planar.
tells us, is this molecule polar or non-polar?
Non-polar.
That's exactly right. You're dealing with a non-polar molecule. So that's how you'd have to figure it out. And I wouldn't worry so much about something like SO3 where the sulfur has like 12 valence electrons.
Okay.
I think if you're okay with going up to the 8 and such, like we saw in the first 2 examples, I think you'll be fine. I think you'll be fine.
All right. I'm gonna try that one. So I know there were some questions on, I thought there was, on saying whether or not, but okay. About their attractions. I just don't know where it's at.
So those would be like,
Is it 6.85?
yeah, the
Yeah,
intermolecular forces.
yeah.
Okay. Sure. Okay, so in terms of your intermolecular forces, okay. First off, you have what are known as dispersion forces. And the one thing about dispersion forces is that they are always present. What's dispersion forces? Dispersion forces are essentially momentary shifts of electron density that even result in nonpolar things for a moment being polar, and that impacting another molecule. One thing you have to understand about covalent compounds is that covalent compounds are made up of molecules of that compound. And if you have like a sample of water, that sample of water has millions and millions of molecules of water associated with it. And there are forces that hold those water molecules together. One thing that's always present, no matter what type of covalent compound you have, is what are known as dispersion forces. They're always present and such like that. Okay. And they are momentary shifts of electron density that results from movement of electrons. And then what happens is that another molecule feels that, shifts its electron density in kind, and all of a sudden you have two molecules that, whether they should be attracted to each other or not, all of a sudden they're attracted to each other. They are the weakest type of intermolecular force. And that means that it takes the least amount of energy to break that force of attraction. Okay. Next, you have what are known as dipole-dipole interactions. And essentially, these are interactions between essentially the charged portions of polar molecules. So nonpolar molecules don't have dipole-dipole interactions. Polar molecules essentially do have dipole-dipole interactions. Now, there's one type of dipole-dipole interaction that's usually talked about different from the general characterization of it. And that's what is known as hydrogen bonding. And what it is, it's the attraction between a polarized hydrogen atom in one molecule and a polarized oxygen, nitrogen, or fluorine atom in another molecule. And in fact, this is the strongest type of intermolecular force. So it's actually a type of it's a type of dipole-dipole interaction, but it's a specific example of it. It's sort of one that has its own terminology as compared to like everything else in dipole-dipole. That's just like a general characterization. All right.
Okay.
All right. So these are the three we have to be aware of. So now we go to letter A, BRF. All right. So if we look at BRF, you have the bromine with 7 valence electrons, the fluorine with 7 valence electrons. So what they're going to do is they're going to share 2 electrons between each other to form a single bond. The biggest question is, when you have two atoms, the polarity of the molecule is dependent on solely the polarity of the bond. So if this is a nonpolar covalent bond, it's a nonpolar molecule. If it's a polar covalent bond, it's a polar molecule. So what you find here is that this bond, based on the electronegativity differences, is a polar covalent bond. Fluorine is 4.0, bromine 2 point something, if I remember right, 2.1. So it's actually like a 1.9 difference. It's pretty big. It's a polar covalent bond. which tells us that we have a polar molecule. So dispersion forces are always going to be present. But is that the major type of interaction? When they say major type, that means they mean the strongest. We don't have hydrogen bonding because we don't have hydrogen. And therefore, what we do have, because this is a polar molecule,
Polar. Okay.
you have dipole-dipole interactions that are present.
Okay.
Now for letter B, KCl, that's an ionic compound. So when you have an ionic compound, what you have between them is an ionic bond. That's the intermolecular force for an ionic compound. So that would be for letter B. I just want to jump to letter D for a second.
Okay.
All right. Cl2. Now again, you have the chlorines with the 7 valence electrons. To get to that magic number of 8, they're going to form a single bond with each other. Now again, because there's only 2 atoms that are present, the polarity of the bond is going to determine the polarity of the molecule. Now, what type of bond is a chlorine to chlorine bond? Well, because the electronegativity difference is 0, a Cl to Cl bond is a non-polar covalent bond, which makes this a non-polar molecule.
Disperse.
And therefore, the only type of intermolecular force that's going to be present are going to be dispersion forces. You can't have dipole-dipole interactions, and therefore you can't have hydrogen bonding because you don't have a polar molecule.
Okay.
Now, just to jump back to letter C, well, this would be NF3. So this would be similar to what we saw already. You know, the nitrogen, now to determine whether the molecule is polar or non-polar, now we have to look at the shape. Because now we just don't have 2 atoms, we have 4 atoms total. So now it comes down to shape. The shape,
3 bonds.
3 bonds, and 1 lone pair. So what does that tell us about the shape? It tells us that the shape is trigonal pyramidal. And therefore, what we have here is a polar molecule. So dispersion forces, yes. Dipole-dipole interactions, yes. But do we have hydrogen bonding? And the answer again is no. And the quickest way to tell is that there's no hydrogen present. And therefore, the strongest attractive force here would be dipole-dipole interactions. I'll just show you one with where hydrogen bonding would be prevalent. NH3. You know, if we put the hydrogen together with the nitrogens, we end up again having a trigonal pyramidal shape. So, and this is, I'm sorry, 6.86D. So dispersion forces, well, trigonal pyramidal shape tells us that we have a polar molecule. So Dispersion forces? Yes. Dipole-dipole interactions? Yes. Hydrogen bonding? Do you have a polarized hydrogen and a polarized nitrogen, oxygen, or fluorine? Well, nitrogen to hydrogen is a polar covalent bond, which means neither the nitrogen or the hydrogen are neutral. They're both polarized. And therefore, the strongest intermolecular force you would have here would be hydrogen bonding. The nitrogen would have what is known as a partial negative charge because it's more electronegative. The electrons are shifted towards it. The hydrogen would have a partial positive charge. I'll just mention this one because it's going to be really important going forward. OH, another classic example of a polar covalent bond. The oxygen, being more electronegative, has a partial negative charge. The hydrogen has a partial positive charge. And I think when we get to our discussions of organic, and even probably within a couple chapters as well, this is definitely going to come up for discussion. I wouldn't worry so much about going crazy with the intermolecular forces. It's good to know because we'll need to have a basic knowledge going forward. But I would say as you prep for the quiz, don't spend like, an hour just focusing on the intermolecular forces. Just have a brief understanding of them and you'll be okay.
Yeah, I think where I was really getting confused was the shapes.
Okay. Yeah, shapes are important. So I would definitely tell you how to figure out shape.
Yeah.
Absolutely.
So then I couldn't figure out any further. So, okay. I think that is all my questions.
Okay. Sounds good. Geraldine, do you have anything? No? You're okay? Okay. All right. No, I can't hear you.
No, you're muted.
I think you might be muted.
There you
Oh,
go. You just
Thank
kind
you.
of
I don't have any questions, sorry.
no problem. That's okay. We just couldn't hear you for a second. All right. Then that's it. Thanks. Stay well. And we'll see everybody next week, hopefully.
All right.
Thank you.
Welcome. Have a good night.
You too, bye.